Materials that affect a magnetic field are known as magnetic or ferromagnetic materials. These are strongly attracted by a magnet and include nickel, iron, cobalt, and alloys made with these metals. When these materials are subjected to a magnetic field for extended periods of time, they become permanent magnets. A permanent magnet retains its magnetism indefinitely unless mishandled.
Let's see how a different material affects the magnetic field.
Notice that this piece of wood has no effect on the iron filings. Materials that can't influence the shape of a magnetic field, such as copper, brass, aluminum, wood, glass, and most plastics, are referred to as non-magnetic materials.
Now, let's see how the strength of a magnetic field can be determined.
Groups of force lines within a magnetic field are called magnetic flux. The more lines of force, the greater the magnetic flux, and the stronger the magnet. A single line of magnetic flux is called a Maxwell. Magnetic flux is measured in Webers, abbreviated WB. 1 Weber is equal to 100 million lines of force. The lowercase Greek letter phi is used to represent the number of lines of magnetic force in Webers. But with Webers being such a large unit, a more common unit is the microweber, abbreviated μWb. A microweber consists of 100 lines of magnetic flux.
You can determine the strength of a magnetic field by finding the number of lines of force in a given area. The greater the number of lines, the greater the power of the magnet.
The determination of a magnetic field strength is known as flux density and is identified with the capital letter B. This is the amount of flux per unit area. 1 Maxwell passing through 1 square centimeter is called a Gauss. As an example, a strong permanent magnet might have a field strength of about 10,000 Gauss. A larger unit of flux density is the Tesla, identified by the capital letter T. The Tesla is equal to 1 Weber per square meter, that is, 10 to the 8th magnetic lines of force passing through an area 1 meter by 1 meter. Use this formula to calculate flux density of a given magnet. B sub T, the flux density in Tesla, equals phi divided by A. Phi is the number of lines of force in Webers, and A is the cross-sectional area of the magnetic path in square meters.
Let's find the flux density for an iron core whose cross-sectional dimensions are 20 millimeters by 30 millimeters and whose total flux is 3 Webers. First, millimeters must be converted to meters. 20 millimeters equals 0.02 meters, while 30 millimeters equals 0.03 meters. To find the area, multiply the height times the width. This yields 0.0006 square meters. The final division yields 5,000 T as the flux density.
The main idea in performing the calculations to determine magnetic strength is to recognize that there are a number of interdependent variables that can affect the relative strength of the magnetic field. Perhaps by now you're wondering what magnetism has to do with electricity. In fact, they're linked very closely. Let's see how.
Electricity produces magnetism. Any conductor that carries an electric current will act like a magnet. Let's use iron filings again. Watch what happens when a wire, which is connected to a DC source, is brought in proximity to the filings. Notice how they're attracted to the current-carrying wire as if it were a magnet. This is because when current flows in a wire, a magnetic field is produced around it. When the wire is disconnected from the DC source, the iron filings are released. The wire was temporarily magnetized by the electricity. The process of creating magnetism with electricity is known as electromagnetism. Look at the word. Notice that it's really 2 words combined, electro and magnetism.
Stop the program and complete activity number 3. When finished, continue watching the program.